All right. So if you've seen me in the club room for like the past like month, me and Alexia have basically been like toiling away, like on a thing called Flare-On. So Flare-On is a yearly CTF run by Google. I guess I'll just pull it up. It's a month-long CTF, which is it's technically still going on, but it's 3 hours left. So it's like, I guess if it's like basically over at this point. Um, so right now, so let me point out a few things. First of all, we're like actually garbage because it's like a bunch of guys finished in like 2 days. How they did that, I genuinely got no clue. We couldn't do it in a month. These guys did it in 2 days. Actually ridiculous. This guy's I don't even know. I don't even want to talk about it. So around 200 people finished it. A little over 200, I think. I think close to 300. Yeah, close to 300 people finished it. We got to challenge 7. We never got. Oh wait, I guess I'm just logged out, but whatever. We got to challenge 7. We never got past challenge 7. For a reason that I'll discuss here. So I'm just gonna go through the early challenges. I have 30 minutes. I'm not gonna go past 30 minutes. So I'm just gonna go through the early challenges and basically talk about my thought process and kind of how I went about solving all of them. Yeah. So challenge 1 is pretty simple. I'm just gonna second. What is it? I guess I'll just run. So the idea behind, let's see if the frog.py works. Oh my god. Do I need to actually do this? Yo, please. God damn it. Okay, there we go. Yo. Oh, what's up, Alexi? Do you want to get up on here? Get up here, man. All right, yeah, this is the clown I worked with. So we're just gonna talk about, yeah. All right, so this is challenge 1. Challenge 1 was real silly. I don't have the original, but basically the idea behind challenge 1 is that this thing was surrounded by blocks, and you just had to, get past the blocks. All you did was just like remove the blocks, because like they just give you a Python file. So all you do is, you just like go in the Python file, just like delete everything, just remove the blocks. And then you just kind of go to the challenge and where is it? Yo, there's the flag. So you just get the flag. That's like ultra easy mode. And at this point, it just like goes up way harder. What is it, like scale exponentially, would you say?
I don't know.
Yeah, pretty much. All right, so that's challenge 1. Challenge 2 was a lot more interesting. Challenge 2, they gave you a Go binary. Let's open it up here. What's up, Lucas? Want to talk about challenge 2? If you want to give it a shot. Do you remember challenge 2?
Sort of.
All right. Let me open it up in Binja.
I don't remember like the functions exactly.
I mean, like,
That was like that one important one, right?
Yeah. I mean, all right. So I guess the key behind challenge 2 was basically I guess I have a Windows machine open, so I'm just going to run it real quick. But that's .NET. Is it not checksum? Is it? Is it checksum?
I think it is.
Where's Binja?
That sounds very familiar.
Yeah, it is checksum. So you run checksum, and yo, yo, that's like ridiculous. I hate Asher. Is that actually what it is?
I don't know.
That's like ridiculous if that's the case. Oh no, checksum's like just like a folder. I'm just like dumb as hell. All right, so if you open up checksum, you basically get it asks you to do a bunch of sums. So I'm not good at math, so I'm just gonna open up a calculator. We just put breakpoints here. We just like change the flags. That's what I did at least, because I was like, I can't do math. You cannot pay me to do this much math. I could have made a Pwn Tool script, but I was like, fuck that shit. Uh, 3954. Let's see if I can get. Okay, it's 66777. They ask you to take like a 1 in 7 math problem. It's actually like ridiculous. Like this is like, I didn't come here to do math. So I mean, you kind of get the idea. I mean, I'll just like do one more just for fun. Oh my god, I have to like scroll up to get to 0. It's like crazy work. 14. You just do a bunch of these maths, and that's kind of like the first part of the binary. But once you get past all the stupid math, you kind of see the checksum stuff here. Actually, where is the string? But yeah, it'll ask you for this checksum, which you saw there. Once you finish that, then the hard part begins. Then it asks you for an actual check. It asks you for, let's even find what the actual string is, but not a valid answer. Like, don't remember where it is. Yeah, it'll ask you for a checksum, and that's why it's called checksum.exe. And you basically have to do something with that checksum. And in reality, what ends up happening here is they like hexdecode it, I think. Yeah, you would put like a hex number, they hexdecode it, and then they do a bunch of crypto on it. So you do some like you have like cha-cha, which is a hashing algorithm. You do, I don't exactly remember exactly what it did, but it didn't really end up mattering, I think.
I don't think that matters. There's like one. I think they're called like one function. Was it a function or just?
Yeah, it was a function. There's like read it writes to SHA-256, then it calculates a checksum. And I believe it compares your checksum with something else.
Compares it against the base64 string.
Yeah.
So it like loops. Where is it actually?
I can go.
So
You should probably speak in the mic.
I know, I probably should. Was it here? Yo, what is this? Why is it so slow? Yo, shut the fuck up. Can we find it?
Wait, you looking at check function or what?
Where's it check?
Check function's right here.
Oh, it's there.
Yeah.
I'm just blind as hell.
Yep. No.
So I think what ends up happening is that it will take your input after it's like been hexdecoded, and then it will like basically perform some operations in this check function here. Essentially,
Right there.
like here.
Yeah.
Yeah, it basically like loops through like your input and does some like, it like reads from this string, like this Flare-on 2024 string right here. Actually, is that it?
Yeah. I mean,
Yeah,
like,
right.
yeah, it reads from this chat.
Yeah, that's like basically just a Flare-on 2024 as a string. And then it does like this like kind of weird operation right here. And then also like over here. And then after that, it basically it just like goes down here and compares your input like these
Base 64.
Yeah, like
first.
or base it encodes it as base 64. And then it compares it here against this base 64 encoded string. So what you had to do is you just like kind of recognize that this is taking in like the input that you passed into that as that checksum. So you kind of just implement like the same functionality. You just like kind of copy this over to like a Python script. That's what we did. And then yeah, you just like pass in this base 64 string here and like kind of do like the same operation on that string. Or I guess I think we like decoded it.
Yeah, you just reverse the string.
Yeah, you just like reverse the string. And then you get like the input you have to pass in into that checksum. And then, yeah, I think that's it.
Yep. I think a few things that are really important to recognize here is that the first thing is that it runs a bunch of checks on your. It runs a bunch of like basically it runs a bunch of crypto on your input, and that can be really scary because it looks like upon first look, if you don't look later, you have to. It looks like you actually have to like find a collision for a hashing algorithm, which is a very hard problem. And I guess the real key lesson here is that once you go forward and you find this check function, you'll see that this takes in the input slice here, and it just basically this just like gives you the answer. It operates directly on your input slice, and if it satisfies this, then you know that your input slice is correct. Yeah. A few other key things I do want to talk about, like Go shit. I guess talk about the Go stuff. Yeah. So this is a Go binary. Go, from a reverse engineering perspective, is notoriously hard. Mainly because there's a few reasons Go is notoriously hard. The first reason is that there's also the reason why Go is used for malware a lot. At least one of the reasons. Firstly, Go Go is always statically compiled, pretty much. So it doesn't really have, well, they basically implement everything that a Go binary needs is implemented in Go, and it's compiled in the binary. So it's not calling stuff like printf. It's not calling any of that kind of stuff. So that's a really big problem, because if you strip your symbols properly, then you won't know what anything is actually doing, unless you do stuff like function signature matching. The other reason why Go is hard is because most disassemblers completely shit themselves when looking at Go. The main reason for that is due to a thing called calling convention. So if you're reverse engineering any binary, there's a thing called calling conventions. Calling conventions are how, when you call a function, where your parameters are. So if you've taken 202, you might know about the 32-bit calling convention, which is where your arguments are always pushed onto your stack in reverse order. So your last argument's pushed first, and then et cetera, until you finally push your first argument. In most 64-bit calling conventions, the idea is that your arguments go in registers. So, for example, in x64 Linux, your calling convention is going to be like RDI, RSI, like RDX, RCX, RA, R9. For Windows, it's going to be like RCX, RDX, RA, R9. And then any subsequent arguments are always pushed onto the stack. Now, the key thing here and why that's problematic is because Go always uses its own custom-built calling convention. And that's a problem because most decompilers here will work off the assumption that this right here is all these functions right here are using the standard calling convention. So, for example, this I1 is the value that is, so if you look at the call, this I1 is the value that's in what? It's the value that's in RCX. Or, yeah, it's the value that's going to be in RCX. But in reality, that's not the actual case. So you actually have to be a lot more careful with Go, and you have to investigate a lot more, and most of the times your decompiler is not useful. So this kind of took us down a massive rabbit hole in learning the Go calling convention. So if you look up the Go calling you can, and I've been meaning to write like a Binja script to because like, you can create new calling conventions in Binja because like, you go to Binary Ninja. This is kind of where scripting becomes useful a lot of times. So we've been using Binary Ninja.
Doesn't support natively?
What?
Binja doesn't support like native Go calling convention?
It doesn't support Go's calling convention. It supports only the standard calling conventions.
Oh, interesting.
Yeah. So if you can actually implement your own calling convention right here, which if you have the time and you care enough to, this is definitely worth your time. Yeah, you can implement your own calling convention. But this is definitely worth your time because otherwise you're just kind of just like hate yourself. So yeah, anyway, the Go calling convention is very odd. It's not like other calling conventions. So first of all, instead of using the standard RA, R9, RDI, RSI, that set of registers, where is it? That is, why am I? There we go. So AMD 64, x86, same thing, uses RAX, RBX, RCX, RDI, RSI, RA, R9, R10, 11, etc. So what that means is your first argument is an RAX, your second argument is RBX, then RCX, and RDI, etc. So in reality, suppose we take I was looking the runtime, yeah. Suppose we take this runtime make slice function, right? This runtime make slice, this 0 is not actually the first argument. Instead, if we look at this assembly, we'll see that this data right here is actually the first argument because it goes into RAX, right? So basically being cognizant of that is important. Another thing that, and actually, if you look at, for example, if you look at the Go source code, which we all spend a lot of time doing, is it runtime dot make slice? Dot make slice. It'll be somewhere in here. You can definitely find it. Yeah, if you look at make slice copy, you'll see that the first argument is in fact a pointer. So you'll see that our assumptions with the calling convention actually match up with the source code, which is interesting. In addition, another interesting feature about Go is that how returning works and how passing structs works. So typically, when you pass a struct in something like C or Rust or any other kind of language, you'll typically pass it by reference. So typically, you'll pass a pointer to the struct instead of passing the actual struct itself. Go actually tends to pass the entire struct. So what they'll do is they'll take the struct and they'll break it down into essentially its primitive components. What that basically means is that it'll, for example, let's say a struct has a long, an int, and a pointer. It'll break it down into its long and an int and a pointer, and it'll move each of those struct members into its own register. So for example, let's say you move that struct, let's say you try to pass that struct into a function. It'll move that long into RAX, it'll move that int into RBX, move that pointer into RCX, I think. Yeah, so to move the fields in order, essentially. Yeah. So that also makes Go really complicated to deal with because yeah, if the struct is sufficiently large, it'll pass by reference. They kind of say this here, which is also really confusing because you actually just don't know. That also makes Go reversing pretty difficult because you don't know if a thing is being passed by reference, well, rather you don't know if something's a struct or if it's just being like, or it's just like a pointer, and like you kind of face those differences. It's kind of odd. Just Go, being Go. Yeah, like Go is generally just deranged. Huh? Yeah. Yeah, it's just like a yeah. So let's see if I can see where it says that, but yeah, they actually describe it here. If T is a struct type, then recursively register assign each field of V. I think they say somewhere that if it's large, then it'll not. Let's see if I can find that. I don't know where it is, but was it? No, maybe I just like dumb as hell. Yeah, I like don't know actually where this is, to be honest. Fuck. Yeah, but the point still stands. So yeah, I mean, those are kind of the quirks with Go. So I guess some key lessons learned here, and I guess I'm almost out of time, but I guess some key lessons learned here were really that, I guess what did we learn? Don't work top to bottom, I guess. If you see something that you probably know, I guess trust your gut one. If you see something that you know is like hard as fuck, skip it and come back to it later. In this case, it was the fucking crypto. The issue with the crypto was that the crypto was basically an impossible problem to begin with. So instead of spending a lot of time on it, it was worth just cutting our losses and just moving forward. That's the key thing with reversing is if you see something that you don't understand, it's probably better to skip it and come back later. In a lot of cases, that's true. I don't know. Anything else? What did you learn?
I guess like the big thing I took away for is like probably like the calling convention that we talked about. Just like understanding that, so like you kind of know like what you're like actually looking at.
For sure.
Instead of getting confused by the disassembler.
I think a lesson that we picked up throughout Flare-On was understand your language. We'll talk. We made the same mistake in Challenge 7 actually, which was just like straight up raw dogging the bind. I'll talk about that later. But so understand your language, understand the environment you're working. Understand the Go convention made our lives a lot easier because we quickly realized that this decompiler output is completely deranged and completely wrong. So we just switched over to GraphView. And we solved it actually fairly quickly from then. So I guess those are the key lessons from challenge 2. So challenge 3, I guess I'll go through the rest of it quickly. But challenge 3, what was challenge 3?
Anger one.
Challenge 3 was, oh my god, challenge 3 was so stupid.
Yeah.
Challenge 3 was also somehow more deranged. So challenge 3 was if you guys are aware what YAR rule, if you've ever done like malware analysis or like threat intel, you're probably aware of YAR rules. YAR rules are basically used to define signatures for malware. In this case, they gave us a big-ass YAR rule that basically described the flag. You have to use something called Z3 or SMT. Basically, the idea behind Z3 is that you basically input a bunch of constraints. So for example, let's say you have like let's say you have like some variable x. You say my constraints are x is less than 3 and x is greater than 1. Give me a value that satisfies those constraints. It'll give you 2. So basically, you basically turn all these into a bunch of Z3 constraints, and then you tell Z3 to go do its shit. So challenge 4 was the web one, wasn't it?
Yeah.
Challenge 4 was the web. I'm not gonna go through this one because it was just kind of silly. You basically found there's basically an alert somewhere in here in the JS. You basically just kind of figure out how to get to the alert. It's basically like a meme. It was like a meme generator, and you basically had to get a certain strings in essentially the slots in the meme. And once you got that right, it just kind of gave you the flag. Anything to say?
Pretty much, you just like line up the images and captions,
Yeah.
and then you win.
Yeah, pretty much. Challenge 5 was what? I actually don't remember challenge 5. Challenge 5 was a fun one. I'm not gonna go through this one too much, but challenge 5 was the Z3 not Z3. What was it?
SSH. The SSH.
SSH bug. Yeah, the liblzma bug. There's basically, this is actually a really good red team tool. I was gonna deploy this, but I never actually like got around to it. But basically, they gave you a stack trace. They gave you a core dump. Sorry. And there's a bug. They basically re-implement it's like not an exact copy, but basically a backdoor in liblzma. You basically have to, using a combination of the core dump and your understanding of liblzma and I guess the backdoor, you were basically able to decipher some shellcode and some network communications, and eventually using that, you could get the flag. That was challenge 5. Challenge 6 was deranged thoroughly. They basically gave you this big-ass Verilog, and they gave you a bunch of test benches. I think all you had to do was what, like change like a single file on the test bench?
I think it was like one character, like one bit you just changed.
Yeah.
And then it just kind of printed the flag.
Yeah, they re-implemented the thing called Blake2b as Bloke2b. You basically changed one character in a test bench, and they gave you the flag. Who wrote this? Dave. Where's Dave?
Right here.
Nah, Dave. This Dave right here.
Yeah,
Oh my God.
you didn't know I can hard hack?
Nah, I'm coming after you, man. So challenge 7. Challenge 7 was, if you've seen us at the club room, and if you, I swear to God, if someone else asked me, have you finished challenge 7? Yo, who asked that? Who asked that? Yo, the door's right there. Yo, have you seen the door? The door's right there. Okay. So challenge 7 was another fun one. Actually, it wasn't very fun, but actually, you know what? It was okay. So if you're aware of C#, so C#.net, typically the normal operating mode for C# is a thing called IL, so intermediate language. So basically what that means is that it'll compile your C# into an intermediate language, similar to like Java bytecode. You'll compile it to that, and it'll run it through like an interpreter. C# has recently implemented a thing called native AOT, which takes your C# and directly compiles into assembly. They give you a native AOT binary, and they tell you to essentially go have fun. So now native AOT binaries are like absolute hell on earth because they don't actually, the way they call functions is all via vtables. So what that means is that, like, imagine if you called printf, but instead of calling printf, they just called this random ass function pointer which you don't know the name of, except that was for every single function. That was basically the hell we were living in. And I guess this comes back to the problem, and we basically like raw dog revert this for like 2 weeks.
Yeah. We're kind of dumb.
Yeah, we were kind of dumb. That was a complete mistake. What we actually should have done is what we did for challenge 2 actually, which is go back and understand C# native AOT. So we ended up compiling this test app right here, and luckily the test app came with a PDB, which a PDB is a Microsoft thing that tells you the symbols for everything. And basically, when you open it up in Binja, you see the all the symbols, which is nice. That's still not everything. So the strategy we ended up going with was, which we never actually ended up finishing, but we have a cool tool that's kind of built around it, which we'll talk. We might do another presentation. We probably will actually do a presentation on the tool we made. So if you're aware in like Java, C#, there's a thing called reflection. Reflection basically tells you the names of all like the objects and all the method names and all that stuff. We basically built out a tool to do reflection, in part because we did this. So that comes back to the lesson of understanding your language, understanding the environment you're working in. Any other thoughts, Alexi? I don't know. I think I'm kind of done here.
I think it probably would have been better for us to try to implement the, I don't know if it's like reflection stuff maybe, or some other like path, just like natively in C#, and then like use like, because then we would already have like the structs,
Yeah.
like all like the classes that we're trying to like implement in this tool, like just already given to us, and then just use that to like right back into like the
Yeah,
full speed, and solve it that way. That probably would have been smarter, but I think this is like a good learning, good lesson to learn.
Yeah.
On like understanding what you should be doing, like,
It's like approaches in reverse engineering.
like your approach.
Yeah. I think you kind of went over time, but yeah, that was kind of it from us. Yeah. I don't really have anything else to say. Yeah, cool. Thanks for watching our terrible presentation. All right. What? That's it. Yeah. I'm like done. Yeah.